Hello, my name is Caden Taylor, and today I'll be talking to you about some research I did over the summer under Maria Sarapoulou and Nikolai Lauk. I will be discussing about how we modeled photonic quantum information processing experiments using Gaussian characteristic functions. Now, to give you kind of an overview of what we'll be talking about is I will start by talking about quantum information processing experiments and why we use photons in these experiments. I will then talk about possible experimental imperfections that can come up and also how we can model mathematically these experiments. I will then discuss 3 experiments in general, which kind of correspond to different imperfections that can come up in experiments. One is called the G2 naught experiment, which corresponds to a measure of photon purity. One is the Hong-Ou-Mandel experiment, which corresponds to a measure of indistinguishability. The last is we'll be measuring the fidelity of a protocol known as entanglement swapping. Now, quantum information processing is the study of how we deal with and process information using quantum mechanics, and it's a backbone for all the quantum computation stuff you've been hearing about. Long-range quantum information transfer is what we're interested in, and it's important for future quantum technologies, such as a quantum internet. You can see us kind of develop this stuff in the diagram on the right. Now, for long-range quantum information transfer, single photons are currently the best candidates for long-distance quantum information transfer. They have low interactions with the environment, and they have low interactions with each other, which leads to fewer losses. However, single photon states are very hard to produce, and we must instead use approximations of these single photon states. One such approximation is known as the coherent state, which is the approximation for a single photon. Another is known as the two-most squeezed vacuum state, which is an approximation of 2 single photons that are entangled, correlated in interesting ways. Now, these approximations cause imperfections, unfortunately. In particular, they are less pure than single photons. Sometimes we can measure 2 or 3 or 4 or even more photons when we detect them, because there are higher number photon components. In addition, 2 single photons are typically indistinguishable. There is no difference between them in quantum mechanics. But in these approximations, we can have issues where differences start to appear and the photons start to become distinguishable, which is not good when we're trying to transfer information. Lastly, we can measure fidelity, which is a measurement of how close a starting quantum state and a final quantum state are after a protocol. Obviously, we want the starting state and the final state to match as much as possible, and so we want high fidelity. But approximations can cause problems with this. To summarize, photons are good for quantum information transfer, but they're also hard to produce, and so we use approximations instead at the cost of accuracy. Now, for experiments, modeling them mathematically is very important, and so we use the math of quantum mechanics to do this. However, quantum mechanics is a bit messy. If we try to use parameters in something known as phase space, we get kind of gross math that's really difficult to deal with. But we can change them into another form known as characteristic functions, which are represented as Gaussian functions. And the good thing about Gaussian functions is that they're fully characterized by covariance matrices and displacement vectors. For example, the coherent state is simply an identity, can be simply represented as an identity matrix and a displacement vector. Now, this is good because we can model transformations that occur within experiments, things that physically occur like beam splitters or linear losses, and we can model them as matrices and calculate new states using linear algebra, which is very, very simple to do. Then we can model how we can detect these states. In particular, we model 2 specific detectors. One is called a bucket type detector, which the math is shown for on the left. Bucket type detectors can either detect a vacuum state no photons, or not a vacuum state, so photons. It can either detect whether photons are being detected or there's nothing. And this is good because the vacuum state is a Gaussian state, so we can quite easily calculate the probability of getting a vacuum state and then the probability of detecting photons, because it's just 1 minus the probability of getting a vacuum state. There's also another more high-tech type of detector known as a photon number resolving detector. And what these can do is they can determine if there's no photons being detected, one photon being detected, or more than one photon being detected, which could be very useful for reducing imperfections. These have to be modeled in a little more complicated way, so we model them as a n-level beam splitter array. The point is, using Gaussian functions, we can mathematically model experiments, which is very, very good for handling imperfections. Now that we've covered kind of the preliminaries in the background, we can start discussing what we found. In particular, we looked at a parameter called G2 naught, which is simply the purity of a single photon source. It basically is a measure of how pure a source is, how much there is a single photon as opposed to higher photon components. And we examined this parameter for two different cases. One is using just a bucket type detector, and one is using what's known as the photon number resolving detectors. And we tried to see if this parameter would improve based on these photon number resolving detectors. And what we found is that when there's not very many losses in the channels, it does improve. As you can see, the bucket type detector, so G2 naught is a measure of purity, and when it's closer to 0, that means the source is more pure. Now, as you can see for the bucket type detectors on the left, there is a clear difference between a bucket type detector and more layers of beam splitters in our photon number resolving detector, meaning stronger and stronger photon number resolving detectors. And you can see that there's a clear difference between the bucket type and the photon number resolving detectors as they get closer and closer to 0 as n gets larger. However, when there's high losses, this is not the case. And unfortunately, there's not much of a difference between purity and whether or not we use a bucket type detector or a photon number resolving detector. We can also graph these in terms of the probability of getting a detection, and we see pretty much the same result. When there are no losses, they're good. There's a significant difference between using bucket type detectors and photon number resolving detectors. But when there are losses, we're kind of out of luck and there's not really significant improvements. So to sum up, photon number resolving detectors help increase the purity of our states, but only when losses are low. We now discuss the Hong-Ou-Mandel visibility experiment, which is a measurement of indistinguishability. In particular, we model it using a parameter known as zeta, which represents the mismatches between the two different photons. In particular, we model this using a fake beam splitter, which splits the photons into different modes of light, which no longer interact. These modes of light represent the differences in the two photons. This model is shown on the left. We can also calculate Hong-Ou-Mandel visibility for more complicated models, such as entanglement swapping, which will be discussed a little bit more later. In particular, we can discuss it for different combinations of detectors, such as 4-fold detections, 3-fold detections, and 2-fold detections, as you can see by the equations below. Now, when Hom visibility is closer to 1, this means that the photons are more indistinguishable, which is better Now, bucket type detectors and PNR detectors were both examined for the simple case. We changed the idler mode from a bucket type detector to a PNR type detector to see how the models would change. And once again, graphing it against mean photon number, we find that PNR detectors are better than single photon detectors in the cases of no losses, which is the graph on the left. However, when we have lots of losses, like we would in normal experiments, unfortunately, there's not really much of a difference. We also modeled the more complicated protocol, which was entanglement swapping. And what we found is for the twofold and the threefold that the mismatch parameter affected the visibility much, much more than any linear loss. It affected it basically at zeroth order for the twofold and fourfold HOMs. Now for the threefold HOM, this isn't necessarily true. The shapes of our graphs are a little different, and this makes sense because for the twofold and fourfold HOMs, we have symmetric systems, but for threefold we don't, and so we expect some differences. But it's still true that the mismatch parameter is much, much more important to fine-tune than losses. We also performed an asymmetry study to see that if we have losses on one side of our protocol and losses on the other side, if they're different, how this changes things. And what we see is that lower losses don't necessarily correspond to better visibility. Instead, what matters is that the two bars of our model are symmetric. And so symmetry is very, very important for all of the visibilities, twofold, threefold, and fourfold. So to wrap up our results that we got with this is that photon indistinguishability is affected more by asymmetry, whether that be asymmetry of losses or asymmetry of the modes themselves. It's affected much more by that than losses. In addition, photon number resolvers don't really help much when losses are high. We now discuss the entanglement swapping protocol specifically when it comes to fidelity. In particular, fidelity is a measurement of how much a starting state and a final state match each other. And within this protocol, which is used for basically reducing losses at long distance, we need to see how fidelity changes. And we kind of combine in our old HOM model in this as well. Now, our results is that we see basically a similar story to that of HOM visibility. A fidelity of 1 means that two states match very well, or they match perfectly rather, and a fidelity of 0 means they don't match at all. Obviously, a fidelity closer to 1 is going to be better. Now, what we see here on the plot on the left is that mismatch affects things much, much more than losses do, compared to the ideal case, which is basically the same thing we had for HOM visibility. And then on the two plots on the right, what we see is that asymmetry also affects things quite drastically. For a while, decreasing losses does not necessarily mean your fidelity goes up. It kind of peaks at two symmetric losses and then starts to dip. And this means that when you have two different losses in the two different arms, there's a high asymmetry and your fidelity actually drops. So fidelity, a measure of how well quantum information is transferred, is more affected by modal mismatch and asymmetry than it is by losses, which tracks with what we have from the HOM visibility case. So we're going to go over all the things we've talked about today, which is that photons are good for quantum information transfer, but they are hard to produce, and so we use approximations at the cost of accuracy. Additionally, using Gaussian functions, we can mathematically model experiments, which is good for handling imperfections. Photon number resolving detectors can help increase the purity and indistinguishability of our states only when losses are low, and both indistinguishability and fidelity for entanglement swapping are more highly affected by mode mismatch and asymmetry than just losses. I'd like to acknowledge my mentor, Maria Sprapoulou, and my co-mentor, Nikolai Lauk, along with Samantha Davis, the graduate student, for helping me with the G2 experiment. I'd also like to thank the entire InkNet group in general, and also the Carl F. Braun Residuary Trust for giving me this SURF, and of course, Caltech student faculty programs. Thank you.